Monday we'll maybe
Monday's a test.
a little bit review.
Next Monday's test 4.
Pretty much.
Next Monday's test 4. The Monday after that, I think, is our final, if I remember correctly.
Yeah, then we're done with it.
And if I were you, I actually kind of like that the final for this class is the first day. Because the more days there are between the last time I see you and the final, the more leaks out your brain, right?
Yeah.
So it might be better to have it
Will
on
we be able to
Monday.
do a little bit review before the final, like if we have a couple questions?
I would say no. Because I want to give you all the full time. And I can't give you more time. Yeah, so we need to get started.
Do you know if it's going to be?
I will tell you how my hours will change the week of the final, so I have a class right before this. So I'll probably have expanded hours early in the morning, but then I'll be given a final right before this class. So the 2 hours before this final, I won't be accessible. So I'll try to have more hours in the morning if you want to come by on that Monday of the final for office hours. Finals week.
And all next week.
And next week will be normal office hours. Okay.
So this is 3.6.
This is 3.6. Yeah.
Alrighty.
So here's the idea. If you throw a ball up in the air, and you all know at some point in math class you hear this type of thing, and what shape would the ball take if I threw a ball up in the air to Candace in the back? And she would miss it because she's eating cookie dough. But what shape would that take as I threw the ball to her?
Like an oval? Or a circle?
I don't know if you guys know. So if I throw a ball to Candace in the back, it'll take a shape like a parabola. In this case, maybe a really fat parabola.
We're all thinking about the actual ball.
Then I smack her and make her unconscious. I feel kind of bad.
Okay. Only trying to.
Just kind of. Because she ate a cookie in front of me and I'm hungry. But here's the point, though. At any time, now I've just drawn a really quick graph. It's not obviously perfect and it's nothing like that. But at every point, this is time. So let's say it takes 3 seconds to get back to her, right? 1, 2, 3, and it smacks her. At each point, I can say at 1 second, where's the ball? So maybe at 1 second, it's up here. You with me? At 2 seconds, where's the ball? It's right here. So forth. So that makes physical sense. What's wrong with the picture I'm about to draw then, if I wanted to make physical sense? What does that picture mean?
That's negative time.
When I say, where's the ball at 1 second? It's not negative time. Be careful. This is time here, right?
Oh, okay.
This is like the height of the ball. You guys with me?
Negative height?
Yeah, and that's okay. Something should certainly burrow under the ground, but the big problem is how could the ball, at 1 second, where is the ball? What is this picture trying to say? It's here and there. Okay, well, that's a problem. You guys with me on this?
Yeah.
Now, trust me, this has to do something with mathematics, not just beyond grasp. I'm trying to make you understand that very often when math people give a name to a type of thing, there's a reason. This is like the most physical reason we've seen. Something we call a function has to be something that I could use to model something in the real world. So if I ask you what size is the shoe you're wearing on your left foot, and you say, well, it's a size 5 and 6. I'm like, what the hell? Are you wearing 2 shoes on the foot? You do that every Monday? What the hell? You guys with me?
Yeah.
So in a lot of physical situations, for a given input, there has to be only one output. I can't say, you know, at 12 o'clock, where were you, Jeff Waller? Well, I was in my office and I was at home. Neat. You with me? So a function is something that for every input, like in this case, time. My input is time. I say at 1 second, where's the ball? At 2 seconds, where's the ball? And the output would be the height. So for every input, there can only be one output. So I'm going to write that down. Anybody ever watch Highlander? There can be only one. So that's how I remember. So for every input, and normally for us that's x, for every input, there can be only one output.
Which is why? Maybe.
Let me make sure you understand. Is this true just in general? No, this is only true for those things that we call functions. In fact, that's the definition of a function. So which one of these is a function?
The first one. The top
Of course the first one, because this guy's trying to say the ball somehow, I threw it, and its twin burrowed into the earth. Right? I'm like, that's exceptionally weird. I know. So, that's the basic idea of a function. Now let me bring it back to a little bit more something that we're used to. Right? That's very visual, very abstract stuff. When we make a table of values, and here you can see it very specifically. Our input is going to be the x. And why do we call it input? Because that's the number that we put into the damn thing. Right? So that's the input. And what's the number that we get out? The y. Right? So normally, now obviously it's not always that way. Sometimes it could be like t there for time or whatever. But generally for us especially, x is the input, y is the output. So for example, for an input of 1, what's my output? 0. Can there be any other outputs? No, 1 minus 1 is 0, right? You guys with me so far? So far it looks good. Maybe it is a function, right? There can't be any inputs that there's more than one output. So an input of 2. 3. Input of negative 2. Yeah. Negative 2 squared is 4. Minus 1? 3. Now this is okay. This is fine. Are there any inputs that have more than one output? 1 goes to 0, 2 goes to 3, negative 2 only goes to 3. It's okay that they both go to the same thing. You with me? It's just that I can't have any x's that go to more than one y. So some of you guys might be thinking, well, how the hell could that happen? Right? So one way I can give you a problem is give you something that looks like this. And let me get a little more specific with my terminology. We call the collection of all of these the collection of all possible inputs is the domain. I'm having a particularly bad writing day for some reason. I'm sorry. How are we doing so far? So can anybody hazard a guess? What would the domain be for this equation? What's the domain? Are there any x's I can't put in? Think about it. And that sounds very strange. But can you think of a number that you're not allowed to square? 0 squared is 0. Right? 0 squared is 0 times 0 is 0. So there is no problem with this. In fact, think even beyond that. What kind of thing is this? Isn't this a polynomial? You guys remember that it's supposed to be good everywhere? So the domain for this guy, so an example, domain of y equal x squared minus 1 is all real numbers. So let me give you one that's not all real numbers. And we had one very recently. What's the domain of y equal to 1 over x plus 2? What do you think the domain of this is? So think about it backwards first. What x can I not use?
2. Negative 2.
Negative 2, right? Is everybody with me?
No.
Because that makes the bottom
0.
0, and I can't have the bottom be 0, can I? So x cannot be negative 2. The domain is everything I can use. So one way to say the domain here is all real numbers except negative 2. There you go. So the domain for this guy is all real numbers except negative 2.
And that's how we answer it.
Yep, that's good for me.
Right? Go on.
Next level of mathematics, you might get a little more precise, but that's good for right now. Nothing major here. We saw that kind of problem back in chapter 6 or 7, I think it was.
Is it negative 2 because x is plus? Because you subtracted two, because the x plus two you.
Yeah, what do you put in there for x that would make the bottom 0? -2. So that's why the domain, don't forget this, the domain is everything I'm allowed to use. So it's much easier on these kind of problems to think, what can't I use? And then say all real numbers except those. How we doing? So that's what the domain is. It's all the things that I'm allowed to use as an input. So there should be a collection of all the things that come out. My outputs, right? And so that collection, anybody know what that collection is called? Range. So the collection of all possible outputs is called the range. Okay. How are we doing so far? Semi-decent? Not good at all? Nothing major here.
So far.
When I have a function, we saw this is our first real example of something that has a problem somewhere. There's an issue with this guy. I can plug in anything I want to except -2. So that's the domain. What we just said is the domain. The domain is everything I'm allowed to use, to plug in. So what would you tell somebody? Oh, you better not plug this in. You would tell them, you better not plug -2 in. So what could I tell them they're allowed to use? Everything except -2. So the domain is a quick way to tell somebody, don't try to plug -2 in there. It's going to freak out, right? It's going to freak out. It would. So when you get to Math 103, 110, you're going to study like radicals a little deeper. You're going to study some other functions a little bit deeper. And the domain is going to include more things. But for us, this is the only real thing we've seen so far that has an issue somewhere. Polynomials are always all real numbers. That's part of the definition. There's no x's in the bottom. It can't have any negative powers, right? So I can put whatever the hell x I want to in there. That was the definition of polynomial. Okay. So let me show you a visual of this. See what you guys think. So don't freak out immediately. We're not going to talk about the functions that necessarily came up with this picture because those are a little bit beyond what we want to do. It's some kind of polynomial function probably. All I want to know is what's the domain and range. Now, can I go below -3? Would this input actually go somewhere? So think about it like that. The domain is the collection of all x's that actually have outputs. They're all the x's I'm allowed to use. So what's the smallest x, the lowest x that actually has an output? -2 has an output. But what else has an output?
I'm confused.
All right.
What?
So for example, what's the output for 3? For an input of 3, what's the output? Do you guys see that? For an input of 3, what's the output? 3. How do I know that? Because the point 3, 3 is on the graph. For an input of 3, what must the output have been? It must have been 3, because that's where they put the point. They being me. So this point 3, 3. Anything above 3 go anywhere?
No.
All right. So the domain can't go above 3.
Or negative.
And the domain can't go below,
Negative.
because the -3 goes to what? An input of -3 has an output of 2.
-2. Is it -2?
So again, domain is the x, range is the y. So the really funny thing is, for any point you can see up here, if you can write the point out, you just told yourself the domain element and the range element. For -3 in the domain, I get a 2 output in the range.
Oh, wait, so it's not -2.
A -2, sorry. I just put,
Oh.
thank you. So we're below there, yeah, so it should be -2. So, does every x in the middle go somewhere?
No.
So, like, yes it does. What about this x right here? Doesn't it go there? Just because I haven't put a little point on it, right, doesn't mean it doesn't go there. Where's this x go? There. Right, so every single x in between -3, let me not freak you out too much, from -3 to 3. Let me write this a little better. We can handle this. We've seen interval notation before. I can write it like that. So that means from -3 to 3. Yes, ma'am?
And that's just the highest and the lowest point of where an
On the
x
x.
is?
So what I often say is I say, if you want to find the domain, which letter does that deal with? X. So I have a little dude walking. What's the first time he sees the graph? -3. He sees it all the way through, doesn't he?
Yeah.
So every single x he's walking on actually has an output because he sees the graph everywhere. Where's the last place he sees it?
3.
All right, now you want to go know the range. So walk the little dude on the y-axis because the range is the output, it's the y's. What's the first time he sees the graph?
At -2.
-2 is the first time he sees it.
What'd you call x? If that's the range, x, y is the range?
Domain.
The x's are the domain,
Okay, I'm putting it together.
and the range is the y's. So what's the lowest the dude sees? -2. And when does he lose sight of it? 3. Cool. That's it. So that means that you can find a point that has an x component anywhere between -3 and 3. So I can find a point, a -1/2. There it is. All those x's actually go somewhere. And where do they go? They go to these values, anywhere between -2 and 3. Cool. Is this a function? What do you think has to happen? Let me see. If a function, for every x, there can be only one y. For every input, there can be only one output. Visually, what would I look for? If it wasn't a function, there should be an x that goes to more than one place.
Is that how you get the pair? Like the 3 and the 3, or like, is that?
No. Is there any x? Like, does -3 go to something more than just -2?
Like if it was like -3 and 1, then that wouldn't make it.
So I mean, if my graph was like this, then this would show me that it's not a function, right? Because -3 would go to more than one place. Does 0 go to more than one place than 1? No, there's no point that goes to more than one place.
Because there's only one line.
And the shortcut, well, you gotta be careful. I could draw a line like this. Woohoo!
Oh, okay.
And that's not a function. The quick way to tell is that 1x, you draw a vertical line, you say, oh, that goes through more than once. That means that 1x value has more than one output. That's something called the vertical line test. You just look really quickly. Does it come back on itself associated with a vertical line? If it doesn't, it's a function. That means every single x has only one output. So this could be the flight path of a rocket. That looks good, Houston. Oh shit. Okay, it's clear now. The rocket can't be in more than one place, but it can certainly go up and down and up. That's fine. But this guy, at time 1 second, it can't be here and here and here. You with me? That is a little bit too neat for a rocket to do. You can argue it exploded, but then I'm saying it's pieces of a rocket, not a rocket. Okay. So, like, for example, would this be a function?
No.
Not a function, because I can draw a vertical line that goes through more than once.
A couple times.
Is this a function? Yes, cool. Because no vertical line goes through more than once. Yes, functions. Cool. Okay, so that's called the vertical line test. It's a visual definition of function. Function is every x can have only one y, which visually means every input can only go to one output. That can't have it go back on itself like that. That's why it's called a vertical line test, to see if it goes through more than once. Okay, now here's the last little piece. This is the meat of the function idea. This is the last little piece. So we had this function up here before. And there's a problem with doing it this way, believe it or not. And we weren't too bad off doing it this way before. But what if I had several functions at once that I wanted to use? You know, I want to use all these functions at once. I'd have to tell people, okay, plug a 2 into the second one, plug a 3 into the first one. I want a better way. They're all called Y. That's kind of stupid, right? There's also another problem. If you plug in a 1 and you do it, you kind of lost sight of what you plugged in. You can't see, once you work it out at the very bottom, you have no idea what you plugged in anymore. You got to kind of look back up there and see what it was you plugged in. So here's an answer to both of those issues. Instead of writing Y here, let's see, you guys are going to love this. You write f of x. And then here you can write g of x. And here you can write h of x. Now they all have different names. So now if I wanted somebody to plug, now here's where the whole thing comes in. This is all about substitution. Right? Don't make it any more than that. If I wanted somebody to plug a 2 in to the second function, I want them to plug a 2 in, right? This is how I would tell them to do that.
Okay.
That says plug a 2 into G. G of x, this is how you read this. G of x. G of x is 3 times x plus 1. So what's G of 2? 3 times 2 plus 1. It's just substitution. Don't make it more than that. That's all it is. So if G of x is 3x plus 1, G of 2 is 3 times 2 plus 1. So what's G of 2?
7.
6 plus 1 is 7. So real quick, what point does the G function go through?
1.
What point does it go through? 2, 7. I can see the input. I can see the output. So see, the problem is kind of like an XY table for you. So you solve 2 issues. You solve, there's too many freaking functions. Let's give them different names. And I forgot what I plugged in. Well, now you can see what you plugged in and what you got out.
Okay. So you would graph that as 2, 7.
Yep, so right now I know 1 point, whatever 7 is, plot 7. Yeah, 2, 7. Yeah.
What if you're trying to tell somebody not to plug in a number for that? How do you write that?
Well, that's not, you
Right.
wouldn't really do that. That would be on the issue of what's the domain, if there's a number you don't want to let somebody plug in.
So there's not really a way to show that, like, in different functions? Like, don't do this for this one, and don't do this.
No, you can. I mean, I don't want to necessarily, you could actually right here say this is only good for x greater than 7. So you're not allowed to use, you can kind of tell people, only use x is bigger than 7.
Okay.
But that, we don't have to get into that. So what would, let me see if you guys can do this. What's h of 2?
Is that 30 minus 2x?
Where would you put 2?
The 5x.
Yeah, here. If h of x is 5x cubed minus 2x, h of 2 is 5 times 2 cubed minus 2 times 2. So I want you to realize it's just like the old problems when I gave you like y minus z squared plus x, and I said, well, x is 4 and y is 7 and z is 2. You just plug them in, right? It's the same damn thing. Don't make it more than that. If here's the g function and I say g of 2, you just substitute a 2 in. It's nothing more than that. This is the way that a lot of mathematics is done. Like if it's a cost function for a company, they would say c of x. If it's their profit function, p of x. Then you can actually relate it to the actual physical thing that it is. Height function, h of x. That makes sense? You kind of see where I'm going. So you can actually do a lot more with this than you could with the old way we did things. You're going to see this a lot in Math 103 or 110, whatever you go to next. So let me give you one thing. I want you to try this at home, and I'll bring the answer key next time.
Want to try this?
Yeah. Weird. Yeah. There's one for you. There's one for front.
So the first one, how do you know?
Z of works and down. Yep.
Thank you. But alright, just real quick.